UK, and he has a very long experience in the nuclear engineering field, both in the US and in UK. Fuel cycle, reactor technology, safeguards, non-proliferations, and so on. And in general, I think he always brings a very interesting, very bright point of view, and always have great comments and ideas. So yeah, looking forward to his talk, and please join me in welcome.
Well, thanks so much. I feel under pressure now to do a good job. So as Max said, my background is pretty diverse and different to a lot of people you may have come across. So I spent 20 years working in the UK nuclear industry before I joined Oak Ridge just over 5 years ago. And I was saying to some of the researchers earlier, I feel very privileged in my career. I've done an analysis where I've seen my own UO2 fuel come off a production line that I designed and that went into a real reactor in the UK. I've seen plutonium fuel come off a production line that I did the design and licensing analysis for that went into a reactor in Switzerland. I was the first person ever to do 100% MOX core analysis for the AP1000 reactor to convince the US, to convince Westinghouse at the time that he had that capability. I've stood on top of the high-level waste store at Sellafield, so people who know reprocessing, they take out the fission products and minor actinides and vitrify them in glass. And I stood on top of the high-level waste store. Beneath my feet was 50 years of waste from reprocessing from not just the UK but around the world, and I'm here to tell the story. So that's a good thing. But I've also done many other things. I've been to Obninsk, one of the secret cities in the former Soviet Union. I've seen their weapons plutonium store. I worked on a whole series of weapons plutonium programs, as well as advising UK government on plutonium strategy. So my interests and background is really, really diverse, and I feel very privileged and lucky to be able to do that. And I feel really lucky and privileged to work at the Oak Ridge National Lab now. I mentioned to Max earlier, obviously all of you would have heard of the Manhattan Project, of course, the development of the atomic weapons. But most people probably don't realise that 2/3 of the entire Manhattan Project budget was spent at Oak Ridge. Most people think of Los Alamos, they think a little more, think of Sandia, the weapons labs. But in fact, 2/3 of the entire Manhattan Project budget was spent at Oak Ridge National Lab. And the reason being is that that's where the enrichment program was developed, that's where the gaseous diffusion, and that's where the calitrons were first invented and tested. The second thing is the first graphite reactor, the first reactor for the producing weapons plutonium was designed, built and operated at Oak Ridge, the X10 graphite reactor. The first reprocessing facility, all commercial reprocessing is based on today, was designed, built and operated at Oak Ridge National Lab. All of the isotope production work that you now rely on for medical isotopes was all done at Oak Ridge National Lab, and all the material science that goes along with that was all done at Oak Ridge National Lab. So when you look at that, it's a phenomenal record, all of which revolves around the fuel cycle. So Oak Ridge really is the true home of the fuel cycle in so many ways, from enrichment all the way through to spent fuel and disposal, and everything goes in between. So I feel really privileged and really lucky to kind of continue my career at the lab. So one of the things that also Oak Ridge is known for over many, many years is the Molten Salt Reactor project, Molten Salt Reactor experiment. And it's really interesting that when I was back in the UK looking at the US, I was not a big fan of molten salt reactors. And today I'm no bigger fan than I was then, but I'm actually more convinced that it's actually a really genuine, true technology that has a lot of potential benefit. There's a lot of hurdles to overcome, but that's not to say it's not going to happen. I think there's a lot of challenges, but it's really interesting to see there's a great deal of new activity in this area, the startup companies and so on. I think it's fantastic. This is truly one of the game changers for nuclear going forward, this paradigm shift in nuclear. So one of the things that people often talk about as a concern, there's multiple kind of challenges that remain in any new reactor technology. Anybody who's read the quotes from Rickover, the paper reactors are cheap, simple, on time, etc. Well, we have to have a reality check, and having worked for the nuclear industry for 20 years, there's a lot of reality in that. But what's really important, though, is that there are some challenges that remain for molten salt reactors, whether it's the corrosion, the material science, the chemistry, the coupled physics, and the feedback that you get there. But also safeguards is one of the things that people often talk about. And I just wanted to include this in the talk because it's probably an area that not necessarily all of you either get involved in or fully kind of get opportunity to think through. So that's why I thought this was an interesting topic. But also, if nothing more, I wanted this topic to be an opportunity to remove the myths behind molten salt reactors in terms of they are a weapons-making machine is not true. Okay. So that's, if you take nothing more away from this conversation, this talk, take that away. These are no more of a proliferation risk than any other reactor technology or any other fuel cycle that's out there. The issue that's really been in this area is that unfortunately all too often molten salt reactors and thorium fuel cycles have been somehow inextricably linked. In other words, all molten salt reactors use thorium and all thorium fuel cycles use molten salt reactors, and that's not true either. And hopefully you'll see that if you didn't appreciate that before. So, what I want to talk through is just some kind of basic fundamental things, again, to give you the opportunity to broaden your kind of experience and understanding before I kind of go into some of the details. So what is safeguards? And why this is really important, there is a lot of misunderstanding, I wouldn't say misinformation, because that assumes people that did it, but there's certainly a lot of misunderstanding. So as it says here, actually, does that work? Sorry, yeah, okay. So what is safeguards? Safeguards is all about the timely detection. The timely detection, that's really important. This is a function of time comes into this, of significant quantities of nuclear material. So this is really about what the International Atomic Energy Agency has its paramount, its prime directive, to make sure that significant quantities are not diverted. So a safeguards approach is a combination of both technical measures, so things like non-destructive assay techniques, gamma signatures, neutrons, whatever it may be, technical measures to detect these significant quantities. But it's also not only technical, but it's also things like concepts and approaches. So for example, how often should an IAEA inspector go in to a facility to inspect, as well as what technology would they deploy once they're in that facility. So, as it says here, the use of material accountancy, whether you weigh that material, whether you measure it with a gamma ratio, whether you use total neutrons or coincidence counting, whatever it may be, there's a series of technology you can deploy in conjunction with what's called containment and surveillance. If you can see what people are doing, that's the surveillance. Containment is things like using seals, and I'll talk about that in a second. So, as it says here, the agency then verified the design information of a facility. Why this is important is that very early on in the design process, which I'll talk about in a moment, one of the roles that the IAEA has is to ensure that if you have a new design, a new reactor design, and you say what it looks like and what its operations are like, then the IAEA's role is to verify that objective and that design is doing what it says and nothing more. So for example, if you say, I'm enriching to only 5%, then they need to verify that you are only enriching to 5% by having a certain number of, say, cascades to your uranium facility and not having more. So it's those kind of things. So as it says, the important thing here is this is about safeguarding facilities, doing material accountability control, accountancy control, that involve nuclear materials. So that's anything that's not just fissile but also fertile materials. I'll come to that in a second. But it does not consider in this the issue of proliferation resistance. And that kind of takes me on to in a second a couple more definitions. So if too far. So if people haven't seen this before, this is where the kind of significant quantities and the masses and the timeliness become really important. So the overall significant quantity is a combination of the type of nuclear material. So is it metal or whatever? Sorry, the type of nuclear material, is it uranium, plutonium, and so forth. The form of that material, so is it metal oxides or is it irradiated fuel and so on. And also how long it takes to convert said thing towards a weapons state. So this overall, these combinations of the type of nuclear material and the form it's in sets the timeliness goal. And then this timeliness goal is an indication of the frequency that the IAEA comes and inspects. So as you can see, this is one of the things I wanted to mention about the proliferation resistance, that as far as the IAEA is concerned, all plutonium is considered equal. It's a really important point because some people have this issue of, is it weapons grade plutonium or is it civil grade plutonium? As far as the IAEA is concerned, it is irrelevant, with one exception, and that is that if you get to greater than 80% Plu-238, then it's no longer weaponizable, and so therefore it goes away as the issue of a safeguard. What's also interesting to note, though, is that if you look at, say, low enriched uranium, less than 5%, 75 kilograms is what they're really looking for. That's classed as a significant quantity. If it's highly enriched uranium greater than 20% or more, then it's 25 kilograms. But what's really interesting is that from the IAEA's perspective, U-233 is classed the same as plutonium. That's a really, really important, subtle point that often not people skim over. But basically, U-233 as a weapons material is as important as plutonium. So anybody who tells you that a thorium fuel cycle is proliferation resistant is so-called pulling the wool over your eyes. That's not true. Because here's the evidence as to what that is. And why that is because there is often confusion between a phrase. Anybody here read any of the papers by Chuck Bafke at Los Alamos on material attractiveness? So if you haven't, there's some interesting papers by Chuck Bafke. So a lot of people read the Chuck Bafke papers on material attractiveness and then associate material attractiveness with safeguards and non-proliferation. And they're all very different kind of shades of grey, should we say, in that. So the way I would define it is dependent on your kind of perspective here, but a number of organisations like the IAEA, the Gen 4 International Forum, and others have developed a methodology by which you evaluate the proliferation resistance of something. They've really defined guidelines, really not specific kind of ways to follow it. Whereas Chuck Bafke and the others, Los Alamos and Livermore and so on, did a lot of work on material attractiveness. And so material attractiveness is really saying on a sliding scale, how attractive is this material? It makes no consideration of whether I'm producing 1 microgram of it or 100 tons of it. It's just that, because the argument is you could scale that up, right? If you can produce a gram of it, well, I just do a lot more and I can produce significant quantity. So they're really just concerned with how attractive the material is, not what a significant quantity is. But what they're missing in that kind of material attractiveness thing is what is covered in the proliferation resistance part of this is the fact that there are certain barriers to get to that material. Okay, so for example, I have plutonium in a spent fuel assembly. Okay, that's got plutonium in it. So from a material attractiveness position, that material is pretty attractive because I've got plutonium in there. But there is no consideration as to how difficult is it for me to get access to that plutonium. So for example, there's a radiation barrier. I'm going to have to chop, dilute, and dissolve that, then do chemical extraction before I get my plutonium. So there's another series of steps that are barriers, either intrinsic or extrinsic barriers to that material. And so this is the way that the Generation 4 International Forum addresses that. They kind of put a value on the material, which is analogous to the material attractiveness, and then they put a kind of number of barriers, which are things like technical difficulty, time and cost, detection probability, and so on. So these things really, the detection probability and detection and resource efficiency, is really what comes into safeguards. Okay, so this is where the barriers, you could argue, a safeguards approach is a barrier to people getting access to the material, and therefore adds to the proliferation resistance. So the way I kind of like get people to think about this is that what's worse? If I've got something that's highly material attractive, very, very fissile, pure material, yet it's very easy to safeguard and know how much of that you've got, is that better or worse than something where it has a low material attractiveness, but I have a lot of difficulty in measuring how much of it you've got, right? There's a dilemma there. And that's the dilemma, that's the two challenges in the differentiator between material attractiveness and safeguards and kind of proliferation resistance. Because the question is, if I can more easily safeguard it, does that make it a lower risk, or if I've got low material attractiveness? So as I noted above, though, the key thing is from a safeguards perspective, all nuclear material, and under the definition of the IAEA, that means those things are listed above, so plutonium, natural uranium, depleted uranium, etc., not just all material that is classed as nuclear. So again, this is the kind of very simple way, very nice, easy way to visualize the difference. So if we are concerned with kind of safety is an easy one thing, everybody can kind of understand and get their head around what does safety mean. But what does security mean? Well, security really is a non-state actor, a terrorist guy, a bad guy, an individual, or a small group. And they're going to do a malicious act on your facility to either cause damage to, cause an explosion to, or whatever, or steal material from that. So that's where security comes in, guns, guards, and gates to ensure that those things don't happen. What safeguard is really concerned with is actions by a host state, by a country, doing things like using its known facilities or unknown facilities, undeclared facilities, to divert material towards nuclear weapons. So this is the kind of the way to simply classify it. Safety, we understand. Security is guns, guards, and gates, making sure that people don't steal material, and then safeguards is measuring and observing what a host state is doing. Okay. So as I said, just that final point here is that I think this is a nice key takeaway. Let's say we're trying to balance off this difference between if I have a material that's very high in fissile quality, but I can easily safeguard it. That's actually not a bad situation to be in. It's actually probably better to be in that position where I can actually safeguard and measure that material versus where I've got some that's relatively low material attractants, but I can't actually tell what's in that facility. So, as I said, there are a number of different kind of tools and techniques and approaches that the safeguards and folks use and the IAEA use. So if we kind of go through, and you can begin to see now where this plays into molten salt reactors. So the first thing that they use is a design information questionnaire. And so what happens here is that a new facility is being designed and considered or about to be built. So there's a questionnaire filled in that the agency can then evaluate and say, yeah, okay, you're going to do this kind of this kind of operation. This kind of facility will need these kind of inspections, and this is the kind of signature we'll use. And then they do a design information examination and a verification. So as you're beginning to build that facility, they will come in and begin to inspect to make sure that whatever questionnaire you completed and said this is how we're going to operate the facility, they can begin to see how you constructed it. You're not hiding pipe work, you're not hiding anything behind the scenes. One of the other things that they do is a diversion path analysis. And what this is all about is that if you are operating, let's say, a reprocessing plant, and we know what your throughput is, and we know what your facility looks like, is there an opportunity by which you are going to do an operation where it suddenly becomes possible for you to divert material in a different way? So it might be going through from one building to the next, or a transportation, or a chemical form change, or a process change. Well, that would be an obvious place where there's a diversion path, and we need to then think about how important is that path, and how can I verify if that path is being used for diversion. So from that, path analysis, that's when we start beginning to define some of the safeguards measures. So one of the things we do is we define material balance areas. So you can imagine that in a reactor, I'll show an example in a second, but in a reactor you can imagine that when the first fuel arrives at the reactor, you can count the number of assemblies, you can verify how much material is in there by doing gamma signatures and so forth, and then you know then that's my material balance area. I know how much material is coming into that area. You also then know how much material is going out of that area, because you can then monitor as a safeguard inspector how much I'm going to load into the reactor every year, and also how much new fuel comes in. So you're basically looking at the flow that goes into and out of and in between those mass balance areas. Then you can define key measurement points that says, well, when there's a change in material or a change in flow or something, that's where I'm going to put a key measurement point. Now, a key measurement point could be something as simple as a weight. I'm going to weigh how much fuel there is. Or it could be something like look at gamma signatures or neutron signatures, as I said. So it can be quite simple, like counting, or it could be more complex, like automated gamma detectors and so on. Containment surveillance, I'll talk about it again, but these things like cameras would be an obvious thing to do, so you know what operations are taking place. So again, using that fuel, the fuel receipt area for a reactor, if you've got a camera on that area, you don't have to be present 24/7 to know what's going on. You can be monitoring that from even back in Vienna, where the IAEA is based, and looking at the cameras if need be. And of course, the other thing as well is a bit like at any point, a bit like with the speed traps. You know, when you're driving around cities, at any point you can be inspected and stopped. Well, that's a bit like the agency does that. Again, they'll do their kind of camera thing and check upon you on a regular basis, but also they'll do it in unannounced inspection. So some of the tools that the inspectors will deploy, as I said, they'll do things like item counting. If I know you've said, I'm going to bring in 20 fuel assemblies, but I can count 20, that's nice and easy. They'll do things like, they'll see the fuel loaded into a fuel shipment container at the fuel fabrication facility. They've seen the fuel go in. They'll take on that container, they'll put a seal on it, and then they don't need to see it again until it arrives at the reactor site, and then they'll be there and present when they break the seal and cut into it. And so the safeguard inspector knows that nothing has happened to that material while it's being transported. So that's what things like tags and seals do. They also have serial numbers on each of the fuel assemblies, so they can track every single fuel assembly if need be, or every drum of powder, or every cylinder of uranium hexafluoride. But also then we have a whole series of non-destructive assay measurements, like I said, using gamma or neutron signatures. For reprocessing plants, they tend to do destructive assays, so they'll take small samples and do assessments of those. A whole range of different things. So, but depending on the facility, depending on a number of factors, it will change which of these is deployed and the frequency and so on. And again, I'll show you an example in a minute. It's much more easy to see that. And again, just in terms of these pictures here, this to show you that during construction, the IAEA are going in, checking that. Imagine for a nuclear regulator like the NRC, they'd be going in checking on construction quality. Well, the IAEA is also interested to make sure you're not putting any hidden pathways in there and so on. But equally all the way through to checking the seals and so forth, and on hex cylinders, or inspecting fuel bundles. So all that's kind of like a bit of hypothetical, but hopefully you can see this at the back. I'll try and point out a few points if you can't. But this is just talking about the mass balance areas, material balance areas, and key measurement points. Some very simple examples. So this is taken from the Loviisa reactor in Finland. So this is just a schematic of the reactor. So as I said before, here's the reactor core. Here's where the IAEA has its seal. This is where there's a canal for the fuel. The spent fuel goes through here via a crane into the racks where it's stored. There's a flask loading area, and this is so you begin to see the kind of classic layout of a reactor. And here's a camera looking at these operations. But what you can then do is you can convert this kind of overview schematic to something that's more like a flow diagram. And so this flow diagram begins to show things like, here's the fresh fuel supply comes into the reactor. We take a key measurement point here, the first one. We have first of all, this whole area, the whole reactor building is one mass balance area. But then within here we take key measurement points. So we do a key measurement point where the fresh fuel's first brought in. Then we take when the fuel goes into refueling pond, into the different sites. Again, we'll go and take a key measurement point there, so we can count for transfers here. It then gets loaded into a reactor 1 or reactor 2, and again, we can do a key measurement point and count there, and then out into the, ultimately outside the reactor. So what this is basically just simply showing is this kind of approach informs on where to measure, where are the kind of transfers, where are the key transfers happening. So where to measure, what to measure. So am I going to measure a fuel assembly, or am I going to measure a gamma signature? I'm going to take a mass, so I'm going to use my my video signal. How to measure and monitor it. So is it like, am I going to use a gamma or not? And the other important thing, which I'll touch on in a second, I'll move on to the molten salt reactor specifically, is even if we can measure and monitor it, there could be some constraints as to whether we can even measure or monitor that. And therefore that may mean that we've got a constraint, a difficulty in that key measurement point. So all of this then begins to lead to, well, do we need to develop new instruments? So let's say, for example, this was a different reactor, like a molten salt reactor, and this was using thorium fuels. So maybe the U-233 signatures that I get from thorium fuel cycles are different to ones that I'm used to seeing in conventional fuel cycles. That would lend itself to the question, do my existing instruments work? Do they work effectively and efficiently enough, or do I need to develop new instruments? Again, the question that I'll touch on in a second with molten salt reactors is the accuracy of that measurement. If I have a large volume of material going around inside a reactor on a very frequent basis, which molten salt reactors, how they operate, maybe there's a change in the accuracy that I need to rely on. So normally if I get a 1% accuracy, is that going to be good enough when I've got thousands of tons of fuel over the history of the reactor going around? Is there a pathway where I can get a protracted diversion? It also then says, well, how often should I be going in, and how often can I be going inside that facility to make those measurements? And ultimately, this all then leads to, do I need to make design modifications to my facility? So again, a very simple example from molten salt reactor might be, if this looks more like a reprocessing facility or a chemical processing facility, is there a need by the IAEA or for safeguards to have hot cells and glove boxes inside that facility. But I can guarantee that the reactor designers aren't thinking about putting the need for hot cells in there for safeguards. So then there's a design feedback that says, hold on guys, if you're going to do this, we need to have an opportunity to measure those things. So we need to maybe make changes to the design of the facility. And just to therefore put this onto a schematic, this is the molten salt reactor experiment. It's a relatively simple schematic, although it may or may not look like that from the back, but here you've got the reactor core, which is, kind of the salt in here, the fissions are going on here and so forth. Actually, the quality doesn't come out very well, but anyway, hopefully you'll get the idea. There's then a pump, the motor and a pump that begins to pump the salt out via a heat exchanger, and the heat exchanger is here. There's also a potential fill and drain tank here that if I need to, either because it's an experimental facility or because of an issue, I can drain my fuel down here. There's also a drain tank, a drain pipeline at the bottom of the reactor, so I can drain that off here. There's a flush tank that once I drain it out, I'll then flush that with salt back through and clean it out and so on. And also there's a suction heat thing, a suction extraction there that's looking at removing the fission product and so on. Without going into the detail of the molten salt reactor, what I just wanted to show is these would be the kind of classic areas where you may think about putting key measurement points. Okay. So we may define, again this is hypothetical, but you may define that all of this is one material balance area, because you're going to say, I know how much material I'm bringing in, that's my fuel salt, and I know how much is coming out because that's my disposal route. So I'm going to put a key measurement point, a mass balance area in the whole thing. Or equally, when you look at this, maybe this is one mass balance area, and then this is a second, and this is a third, and maybe these are the relevant key measurement points. So all I'm just trying to illustrate here is that this is not being defined for molten salt reactor experiment, but this is just the kind of thinking you would have to go through, and this is what we're currently doing for the molten salt reactor concepts that are out there, is to begin to define what measurements do I need to take and why. What do those measurements look like and why? What uncertainties do I need on them and why? What are the instruments that I can deploy today or do I need to develop? So the important thing for anybody who's not really been following the molten salt reactors is there is no such thing as a molten salt reactor. There's molten salt reactors, plural, okay, and hopefully this diagram shows that, because there's a guy I work with, George Flanagan, great old guy, I call him the Gandalf of reactors, because he's been around forever and he's so knowledgeable. And George has this great phrase where he says, these molten salt reactors are not your grandfather's molten salt reactors. And what he means by that is that these MSRE and the molten salt breeder reactor and all these other concepts from the 60s and 70s are not those systems that are being deployed today. Those systems being deployed today are so different in so many different ways. And this diagram, it kind of begins to trying to illustrate that. So these colour scheme here is just indicative of an illustration of the different the different concepts that the developers are working on today. So you've got the European Molten Salt Fast Reactor Terrestrial, Kairos just down the road here, Moltex in the UK, Fly, Transatomic, TerraPower, etc. The MSRE and the old aircraft reactor experiment, which is the basis of the MSRE, are in there as well. So they all appear in this box here because they're all molten salt reactors, right? But the question then is, some of them have got liquid fuel. So in other words, the fuel is part of the salt and that's going around to cause fire. In others, that's not the case. It's a solid fuel and the salt is just a coolant. Okay? But they're both still classed as molten salt reactors. So instantly now the safeguards mind paradigm is different, right? One's solid fuel, one's liquid fuel. Big changes. Again, in some of them, in these fluoride high temperature reactors, there are different fixed fuels and some moving fuels. So again, the Kairos one has a moving pebble fuel. In other concepts, they have fixed fuel that just doesn't move. And again, so this just illustrates the variety, but also the depth. So this is showing you the fuel form. This is showing you the whether it's moving or static fuel. This is showing you the range of fast spectrum, thermal spectrum, time varying spectrum. So this is all varying in spectrum. This is also illustrating types of different fuel, LEU or thorium. Fuel salts types, whether it's chloride or fluoride, different non-salt coolants, even some of them have got lead and sodium as a coolant, which is like bizarre. It's like combining every combination of fermentation. But these things are really being, actually lead doesn't exist, but sodium does. And then also over here, then looking at the fuel cycle, what's the equilibrium fuel form that's going around at any one time, and also whether there's any separations, active or passive, or just fission products being removed and so on. So my point is, hopefully this point illustrates one thing. As I said, there are so many variants of molten salt reactors, so any concept we come up with for the safeguards approaches of molten salt reactors is highly unlikely to be the appropriate one for all of these. So we have to pick and choose which ones to look at. So we're doing work at the moment for the NNSA, looking at a sample of these, which I'm not going to point anyone, I'm not supposed to say. But anyway, we're looking at some of those over there in that box. So we're not looking to try and trip them up or anything else. We're trying to help them and inform on their design. So, all that said, what does this mean? What it means is, what's the difference between light water reactors and molten salt reactors? Well, first of all, we have what we call traditional safeguards today, because that's what we do every day. Everybody around the world in the IAEA community knows how to do safeguards at this site, but this is likely to be non-traditional. What do I mean by that? Well, we routinely apply safeguards today, but these techniques and approaches and instruments are unlikely. It's not proven, that's what we're doing right now. There's going to be a proportion we can use of the approaches, a portion of the technology we can use. In light water reactors, of course, the reactor and the fuel cycle facilities, like our fuel fabrication or our reprocessing and so forth, is under different facilities, and they're distinct and have different safeguards approaches for each of those facilities. In a molten salt reactor, in most cases, the reactor and the fuel cycle facilities, or most of the fuel cycle facilities, will be under the same building in a single facility. That has benefits and disadvantages, some of which we need to figure out. Most of the IAEA's assessments are done based on counting discrete items, counting number of fuel assemblies, barcodes on fuel assembly 1 and fuel assembly 2, differentiate those two fuel assemblies. And refueling is done offline. But, of course, as we said, if you look at the fuel salt, particularly those ones, if you look at the MSRs, particularly those with fuel salt, that salt can be a mix of all sorts. The fuel salt, coolant salt, fission products, actinides, online refueling, potentially a lot more complex, much more like a reprocessing facility, one could argue. And this is much more, therefore, like a discrete versus a bulk processing facility. So again, similar kind of things, this is the kind of thing we would use. Additional monitoring may or may not be appropriate. So the key thing here is that there are going to be a combination depending on the reactors and the particular concept being considered. Molten salt reactors share characteristics of both the reactors, so in other words, we are transmuting fertile or fissile material into a nuclear material. But we're also doing some form of spent fuel processing. It says reprocessing there, it's not necessarily reprocessing as you would normally think. So most of those systems I showed you in that previous slide, what they're only doing is they're only removing things like fission products or rare earths. They're not removing pure streams of plutonium. So that's a big difference. When in a reprocessing plant, we remove pure streams deliberately. So. But of course, the problem now is that we're not just doing this piece, we're doing this under intense heat and radiation. So again, think of a reprocessing plant. How long, people know how long it is before fuel is reprocessed in a reprocessing plant? How many years cooled is fuel in a reprocessing plant? 5, 10, 15, 20 years cooled, right? So all your short-lived fission products, your high emitters of radiation and heat, have gone away, primarily. Not all of them, but a good portion of it. In a molten salt reactor, it's potentially seconds or fractions of a second or minutes old. So we're going to have to deal with that. So how long are your electronics going to survive in that kind of bad environment? Possibly not really. So we need to be doing a lot more work in that area. As I said, unlike in the reactor case, the nuclear material may not be in a solid or a fixed form. It's kind of changing, it's moving, it's evolving. And so we need to think about this more like a reprocessing facility or more like a uranium conversion facility. But again, needs some thinking. And the other thing as well is, though, again, this is the potential advantage of a molten salt reactor versus a reprocessing facility. is that if you think of a reprocessing facility, we have a box here, we bring fuel in, we process something, and we have an output that comes from that. In a molten salt reactor, more often than not, that's in a contained box. We bring salt in, yes, but we take nothing out other than electricity, and we'll keep everything in there. All of our fission products will store and maybe contain, and then, or we'll contain and then maybe overpack and produce into a form. So it's almost like a closed loop. You know, the salt kind of goes around within the reactor loop for sure, and any fission products removed, they can stay within that box. So again, it's a little bit different in terms of mindset that may result in its own challenges. So as I said, some of the challenges we're facing are things like homogeneous mix of fuel, coolant, and fission products. We're going to have to now pick out signatures from all of that. Is that going to be easy or more difficult? Maybe there are unique signatures we can look for. That's one of the things we're trying to work on right now. There's a continuous variation of isotopics. This is really important where things like the inventory calculations that are being used, it's not as though any of these reactors have like a constant fuel, because we're going to be loading in, say, a fertile material or a fissile material that's going to be converting and changing all the while. So there's almost like a time variation as well as a physical form change we need to be aware of. As I said, very challenging environment, high operating temperatures, high neutron and gamma flux, corrosive. So there's, again, challenges there without much thinking. Potential for online reprocessing or chemical processing of some form, maybe, but not so many people are doing that. But you can remove quite a percentage of the core for either storage or for fission product removal. Again, unique refueling, we may be loading fertile material as well as fissile material at any one time. We need to be tracking that. But the other thing as well is we haven't just got all those things just in the reactor core. We've got them all over. Namely, we've got them going out to the heat exchangers and the second, or maybe not direct into the secondary side, but certainly into the heat exchangers. We may have kind of fission product removal systems, rare earth removal systems. Well, none of those removal systems are going to be 100% effective and efficient, so there could be some carryover of fissile material into those streams because of volatility and so on. So therefore we have to monitor all of those streams. So the fissile material is kind of like everywhere. It's in storage tanks, it's in heat exchangers, in the cleanup system, it may be outside the reactor vessel in storage containers. So we're going to have to think about all of those areas we need to monitor and measure. And of course, the other thing as well is that at any one point when we shut the reactor down for an outage or maintenance or whatever else, then the solid fuel, the frozen fuel, becomes an issue as well as liquid fuel. So we need to prepare for that also. And as I said, on some of the systems, they're actually talking about storing the fuel outside of the vessel for long periods of time at the reactor site for potentially starting up a subsequent reactor. So again, something to bear in mind. So again, I've probably touched on some of these already. We need to look at these designs to figure out what the instrumentation needs are. The interesting thing is if you think about, let's say for example, I need to detect one significant quantity, which is like say 10 kilos of uranium. You know, if I've got a 1% uncertainty, yeah, I can kind of see where I've got 1,000 tons and I've got a 1% uncertainty. I can get my kind of one significant quantity. That sounds about right. But if you suddenly think I'm going to process a lot more salt, I'm going to be processing thousands of tons of salt that are going to go around the loop at any one time. Do I need to now have a much higher level of accuracy on every one of my measurements? We don't know. It depends on what the safeguard inspectors think. As I've mentioned already, we may have unique signatures here. Maybe we can use those unique signatures in a different way. That's one thing we're investigating, whether you can use like fission product signatures as well as for operations, as well as using signatures from the uranium and plutonium. I've already mentioned the high thermal radiation environment. Reliability issue becomes really important. How long can these instruments operate? How can I get in there and maintain and operate those things? How frequently can my IAEA inspectors get in there? Can they go in when these things operate and whatnot? So there's an extensive assessment kind of required here, and that's one of the things we're working on at the moment, is to look at how much of today's technology is viable or not for the future, and how much is new is needed. And some of that new could be fundamental changes, others is still using the same instrument in a different way. So all of that said, this kind of begins to point to, well, why do these new startup companies, in a sense, need to listen to this and think about safeguards? Because they've got so many other things to think of. I'm not saying that safeguards is number 1 or even number 99 in their priority list. There's plenty of other things they need to worry about. But certainly, there could be a potential implication on their design of their reactor. And we better darn well figure that out early rather than later. So that's what we're saying here, is that there's this thing called safeguards by design, and the idea is that if you can, then in the same way you have inherent safety, it's just a natural thing, everything's going to have inherent safety features in our reactor. Well, what we're talking about here is the idea of having inherent features that enable the safeguards to be conducted much more easily, much more straightforward. So build that into the design. So the possibility of new nuclear facilities, should we be introducing them early, these new concepts, these new approaches, most definitely. And as I said, it's similar to safety features that we just build in today. We don't even think about it. So it's really the idea here is trying to save money. Okay, so if we can design something in today that makes our operations much more effective and efficient, where we don't have to be shutting the reactor down to do safeguards, we don't want to be interfering with their operations and slowing the processing down of material. We want them to be effective and efficient, then this is what we're talking about, is we need to make sure that all those things happen. And so when you look at it, everybody kind of advocates this idea of safeguards by design. So it is important because if anybody's tried to retrofit anything, you realise how difficult it is. You try and put a new exhaust concept on your existing car, and it's not quite the exhaust, it doesn't quite fit, the bolts don't quite line up well, that's pretty complex. So this is one of the things that this safeguards by design gives you, is that you do that up front, because retrofitting can interfere with operations. Imagine having to then go back in and stop the reactor and start putting new measurements in. That's not a good idea. You've got issues over radiation protection, and also maybe introducing these new concepts could affect the safety parameters. So the objective here is for the designers and the researchers like ourselves to work with the regulators like the IAEA. So I was over at the IAEA earlier this year talking to them about molten salt reactors and advanced reactor concepts as to some of the things we need to be doing and thinking about and getting the IAEA to advise in the appropriate way. Recognising that monitoring may be different, may need to do remote sampling, so you might be able to have to go in there and do things a little bit differently. Maybe reduce the quantity of fuel outside the vessel so we don't have this issue of material being diverted, and also maybe providing accessibility for inspectors. So this is basically what we're saying here is that anything that we do needs to be thinking about the IAEA and what they're trying to do there. And what's really interesting from a kind of US perspective, people say to me, well, if I'm going to build one of these things in the US, we don't need safeguards, right? Because we're a weapons state. No, that's not quite how it works. So the first thing is that most of these techniques that I'm referring to are equally important for things like material accountability and control. In other words, things like criticality safety. Knowing where your material is at any one time is really important, right? But as I'm doing for safeguards or for safety, it's really important that I know that. So there isn't a reason. But the other takeaway here is that the safeguards, the new countries looking at nuclear, they really see safeguards and the ability to do safeguards as important as safety and economics and so forth. Because they realise that if they've got two designs, this one can be safeguarded, this one cannot, there is no way the international community is going to allow them to build that one, the unsafeguarded one, right? So all these startup companies in the US and new ideas, they realise that there is a domestic market here, but there's also a large international market. And so that international market has got such an eye on safeguards, as the IAEA has, that they have to make sure this is all built in. So as I said, why should you take note as a vendor or as a developer? Well, they should take note because these new countries are going to want it, but also the IAEA will be insisting on it. Of course, the strong negative impact on the overall MSR concepts and designs if there's a perceived safeguards. If you can't safeguard it, or there's a perceived risk that you can't safeguard it, then that could potentially have a negative impact on the market for these things. They may have technology challenges, but we can overcome those early by doing some work in this area. That's what we're all working on. So some of the key questions that need still to be addressed, and these are a series of questions that I put to the IAEA at a recent meeting I was at talking about this topic. So, question is, this is a nice way for people to frame research. Sometimes it's not easy to give the answers, but it's nice to frame it by way of questions. I'm not sure that's what you've ever done that. It's quite an interesting way to kind of frame your research. So the question we ask is the IAEA, the International Safeguard System, ready for MSRs? And if not, what steps should be taken? What do you think the answer to that is right now? No. So, member states should be approached to help develop the new nuclear material accountability verification methods for molten salt radiative fuel. So that's what we're doing right now. So we're trying to address that gap. Second question, are the safeguard inspection regimes of today valid for proposed MSR designs and the associated fuel cycles? What do you think the answer to that is? No. Again, I've already pointed out the IAEA has little experience on these kind of designs and so on, so they need to get their head around exactly how you would go about inspecting these. Have the appropriate safeguards approaches been determined for molten salt reactors? I think the answer is no. Are the safeguards approaches for one MSR design valid for another design? No. Are the safeguard inspectors today aware of and prepared for the challenges presented by MSRs? Partially, because I went and told them. No, that's not quite true. But they are partially because they are aware that the molten salt reactor community is growing. There is a potential international interest in molten salt reactors, and so they are doing, due diligence, we say, early kind of not evaluations in the true sense of the word, but certainly beginning to better understand. We're helping them try to address that. Is the safeguards technology today sufficiently mature to meet the verification challenges posed by MSRs and associated? Again, more is needed. And are non-destructive assay technologies of the measurement instruments ready for deployment? No. Because it may, I guess that could be a maybe, because we're not quite sure yet, we don't. So the key thing here is that there are a number of challenges remain and there's uncertainty, but they can and are being addressed. That's a good thing. And that's why I want to take away from this, is that there's a lot of misinformation out there as to what safeguards is, what non-proliferation is, what kind of material attractiveness is. All those things are very, very different. People get their heads spun around what each of those means. I'm talking specifically about safeguards. But there are challenges remain. There are a wide number of variants, all with different challenges, because they've all got different fuel cycles. But we're going to figure that out. The associated fuel cycles, all this isn't really well documented, it's not understood, but it's being addressed. We are working with molten salt reactor communities, we are working with the IAEA, we are working with the NNSA, we are working with the National Lab Complex, and the National Programme of Molten Salt Reactors, the one that's headed out of Oak Ridge to address all of these things. So this is kind of an indication of the kind of papers that I've been talking about. Safeguards approach to instrument used in the field today are unlikely to be applicable, so we just need to do some more work to figure that out. And again, that's one of the things we're working on now. So basically, just choosing one or two designs, going through a full safeguards approach, and understanding what kind of differences there are, and then from that identifying the gaps, and then from that identifying the roadmap. But in fact, this kind of thing doesn't just apply to the molten salt reactor community. This is true of any other advanced reactor. Again, if anybody's worked in the kind of pebble reactor concept, how uniquely identifiable is a pebble, and do you need to do that? Well, that's a challenge, right? It's probably a similar kind of thing. So it's not just that there's nothing particularly unique about molten salt reactors in that sense. The other interesting one here is that there's something called it's in Circa 540, which is basically a list of technologies that says if you see this technology coming across your border, then be aware that this may be an indication of nuclear activity. So there are likely to be specific materials or specific technologies associated with molten salt reactors that the IAEA and other people are not used to seeing. So for example, if you were at a border today and you saw FLIBE come over your border, you might look at it and go, oh, I have no idea what that is, that's not nuclear. That's fine, because no nuclear reactors have FLIBE in that. But on the other hand, if it's FLIBE in the future, that might be an indication of, well, this country is developing a molten salt reactor. So this is again a gap that needs to be addressed as we begin to move forward. But the key takeaway here is, and again anybody who's read the Chuck Bathke work and anything else on this, is that the long and short of it is all of these reactors, whether it's a light water reactor, whether it's a CANDU reactor, whether it's a sodium fast reactor, whether it's a molten salt reactor, every one of them needs safeguards. Because as soon as you have nuclear material, not just fissile nuclear material, but any nuclear material, uranium, so forth, thorium, they all need to have safeguards in place. So what we're just doing really is figuring out what's different about the molten salt reactor tech variants and how there are maybe some cross-cutting things that need to be developed and deployed and lessons learned. And then we'll work on developing those further. All right, thanks so much. Happy to take any questions.
Questions? I'll start with a question. So the attractiveness, the material attractiveness at equilibrium, I would agree in general, is relatively low for any of the systems. But some of the systems in the transition time, below the equilibrium, have very attractive materials. So do you think that that would change the requirements and the case for safeguards?
Good question. So the first of all, even when you're in equilibrium for material that's considered less material attractive, you will still need safeguards, right? So safeguards will never go away. Just make sure that people understand that. That safeguards will never go away, but always needed. The question that probably begs though is that, is there something uniquely different about the signature during the transition or the mass flow or whatever it may be that's significantly different? If the answer to that is yes, then that may change the safeguards approach. So that safeguards approach could be, let's say for example, if at equilibrium I'm relying on a certain signature that only exists at equilibrium, then I'm going to have to change my detector time. So it could be at that level. But equally, it could well be that in the early days when you're kind of transitioning and I've got good quality plutonium, then maybe I just need to do my inspection and my measurements more frequently. So that could be a relatively simple change, because the safeguards approach therefore could be a technology change or a frequency of inspection change. But what that actually looks like and how frequent that is, that's why we need to, and that's back to that point I made. It's really important, this inventory, the ability to calculate an accurate inventory throughout time, so throughout the reactor operations, because there's no such thing really as an equilibrium salt, as you know, it's always changing. But also, so you need to monitor through the reactor's lifetime, but also through the salt's journey through the reactor, because there could be potential biological pathways in there. So therefore, predicting the inventory as it flows around the reactor and as it moves through time is vital to this.
Chris?
You mentioned that it's important, or you emphasized the importance of including safeguards in your design at the earlier stages to minimize economic impact. I'm curious about deriving economic benefit using safeguards if you're informing instrumentation or monitoring strategies. Is there some kind of symbiotic relationship that can be cultivated? Is there anybody working? That's my first question. And my second sort of comment is that like one example I can think of is that if there's a central regulatory body like the IAEA that's collecting this data, then they may be able to perform some kind of analysis on that data that may be privileged information for each individual reactor, but they may be able to put out analyses that are useful then to the operations of those reactors after the fact.
Yeah, so in terms of the second thing is the agency doesn't share data back. That's
but it's not a data, like they don't have to give the basis, they can just give the analysis.
Yeah, that's true. I mean, I guess it depends on what they need that data for, so that the agency is not in the, well, certainly the safeguards part of the agency is not in the business of improving operations of a reactor. Unfortunately, I see where you're coming from. If there was a potential to have feedback, that would be beneficial. Just that's not the agency there. But anyway, back to your other question. Back to your question about whether there's some kind of symbiotic benefit. I think the answer to that is yes, because if you look at the need from a safeguards perspective, I need to know how much material I've got, where it is, what form it's in. Well, all of those things very much align to how well is my reactor operating? Is it operating like I think it is? Is my material where I thought it should be? And am I removing, say, fission products as efficient as I thought I should be? And you could even look at that maybe as a, one of the things we talk about is there some way maybe of using that almost like a power monitoring system? Because fission products and power will scale directly, right? So if I can measure my fission products, then I might. So there's some symbiotic relationship there, but the important thing is though that system that I deploy for safeguards cannot be the same system that's being used by the operator. You may have a shared point, but that data point has to come off independently and go somewhere else. You can't share it in the truest sense. But if you're developing an instrument as a researcher, you can definitely see potential for them to go either as an operator benefit or as a safeguard benefit. Sorry. Yeah.
So basically, before you send list of questions to International Atomic Energy Agency, there is one step before that, which is who will license these reactors. In this country, it's the Regulatory Commission. So are they ready for it? So this is entirely
That's a very good
different question.
I think, well, so back
Because
to
they have to address a lot of questions.
Oh, they do. So back to the kind of the three boxes I had, you know, safety, security, and safeguards. They also need to address the safety box and the security box and the safeguard box. So the answer to your question is the NRC ready?
No.
And so the good news on that though is that earlier this year, actually I mean last month, Oak Ridge has been running a series of seminars for the NRC to begin to bring the NRC up to speed. And actually all of that material, as I understand, will be made publicly available. So if the teaching classes and so on, so it'll be a really good resource. So this is basically taking the expertise from across the lab, from the MSRE experiments, operation experience, and all of that is being captured into educational slides for the educating NRC, but it can be education in the public or students and so on.
But you also can gain a lot of information from monitoring the processing facilities.
Yeah.
And there are several in several countries, so something similar.
Yeah, exactly. And I think that the important thing in terms of the molten salt reactors versus the reprocessing facilities is that obviously the environment in which they're in is very different. As you know, in terms of the heat, the dose, and so on. That's one thing. But also the things we'll be looking for could be notably different. You know, for me, I have this hope, this belief that one of the things we'll be looking for is a unique series of signatures that we don't normally look for. So, for example, anybody who's done any burnup analysis, you always look at cesium ratio. That's a classic one. That's great. But maybe, and I'm not going to go into detail right now, because I want to put a patent there. But anyway, I'm convinced there are going to be some unique other signatures about ratios that these short-lived fission products give you that you don't normally see. So it's a pretty interesting challenge. But then you've got to develop the detector to see the damn thing. That's the problem.
Any last question? Okay, thank you. Very interesting.